Phys 2111, 2211, Lab 3. Let's get into it. So for this lab, the goals, we have two main goals for this lab. One is to find the mass of the black hole using a computational model and a given mass of the star. And then for the second part, their goal is to find the initial velocity needed for a spaceship to fly close to the black hole before escaping the black hole planet system. And once again, we're going to find this by using a similar computational model. As for the findings, you see, I put them down here. So for the mass of the black hole, we had 8.22 times e to the 23 kilograms. And then obviously our initial velocity for the spaceship. For this lab, we the fundamental principles that we need to know. Um, Obviously, we need to know Newton's second law, which states that the net force on an object is the change in momentum over the change in time. And given this, we can it can be rewritten to show the velocity update as well as position update formulas. We need to know the gravity formula to find the force of gravity, which will, later lead to us finding the mass of the black hole, as well as the force formulas for perpendicular and parallel forces. So how to find those two. For part one, these are the initial conditions. The system is the black hole and the surroundings are the star. Obviously, we were given the mass of the star, which was 2 times e to the 30th. And for our calculations, we used the forces for the parallel and perpendicular, as well as using the gravity formula, which was able to give us the mass of the black hole. And so as a result, these are the net forces found, parallel and perpendicular, as well as the net force, and then the mass of the gravity of the black hole at the bottom, which is 8.22 times e to the 33. For part two of the lab, once again, we had a system. Our system was the spaceship, and the surroundings were the black hole. So these are the initial conditions put into place. As far as calculations, we wanted to find the force of gravity acting on a ship by both the planet and the black hole, and I utilize as well the velocity update and position update formulas to find the initial velocity needed of the spaceship, which was in the x direction -4.e to the 7th, and the y 2.5 times e to the 6th, and z0, of course. As far as possible sources of error, we have the potential rounding errors, which are always going to be present, and then as well as the black hole mass not being constant. So I forgot to mention this earlier, but when I ran the simulation for the to find the mass of the black hole, the numbers were pretty much like they kind of fluctuated, but they all stayed around the same. So I took like an average. But given the fact that I didn't get a set number, there's potential for there to be error there. For the what does it mean question, so the question asks, how does the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? So once again, Newton's second law lets us know that these forces are the same, meaning they're both, F net force. But in order to find them, we have to use different calculations. So for the rate of change of momentum, we see that, F net equals dp dt, which can then be rewritten to equal mass times delta v equals delta t, which then can be further rewritten to equal mass times acceleration, which is, the famous formula F equals ma. To find the F net from parallel and perpendicular, it's similar in a sense, but also different because you have to find a dp dt for the individual of both parallel and perpendicular. So if you find the F net for the parallel and perpendicular force, then those two can be added together, and that will give you F net. And for my what if, instead of taking a quick look at the black hole, they decided that they wanted to enter the orbit. So what initial velocity would we need in order to enter some kind of orbit around the black hole? This was just trial and error. Just plugging in numbers that's similar to the ones that I got. And I was able to get velocity that finally worked, that I've written down right here. And yeah, that's the